Okay, time to get started. So let's see. Before we get back into the math, and this is where we left off last time, I just want to remind everybody about the homework schedule. So recalling that this is on our section Sakai site, so the one for my sections, not for the whole course. The tool is called the lecture schedule on the left there, and all the information you should need about the homeworks, or organizing the homeworks anyway, is right here. So homework 1, you'll see, we're almost done defining homework 1. The remaining cell to be figured out is this one right here. What we will finish today, of course. Keep in mind every row corresponds to a class meeting date. What we finish today is what will go in this cell. I'm expecting it's going to be 1.3. And so all of the sections listed here, all of the questions outlined on the content syllabus for those sections are all due as homework 1. And the due date, of course, you see here as well, also listed. So Friday, January 20th, so that's the day after tomorrow, right? And note that the time for all of the homework due dates, always 11 p.m. That's Durham time. Okay, so let's see here. The other thing I was going to mention on that. Oh, yeah. So I would, if I could, go ahead and create the Gradescope items that you'll upload to far in advance. The problem is I can't, because the way we have it set up, the Gradescope item that you'll upload to has to tell Gradescope what exact exercises to expect you to submit. And I don't know yet, because it's not entirely clear what we're going to have finished by the end of this last date, until this last date, namely today. So my expectation is we'll have the Gradescope item created by either this evening or tomorrow morning, something like that. So that'll give you a comfortable, let's see, what would that be? 36-hour window, at least, I would hope, to actually make the submission. So start looking. If you're ready to go and you want to get it submitted, then you can start looking. Tonight or tomorrow morning. And if it's not up by the middle of Thursday afternoon, something's gone terribly wrong. Please do me the favor of emailing me and letting me know, because that would be bad, and I'd have to get that fixed. Okay. All right. Any questions about homework submission? Logistics? Everybody's comfortable? All right, back to math. So, last time we were talking about the difference between parametrizations and equations. So a parametrization generates points, whereas an equation doesn't. An equation tests points, doesn't really generate anything. And likewise, a parametrization doesn't really test anything, it just generates. So these are different functions, and so let's see here. So sometimes this is actually a good thing, and this example here is demonstrates this convenience. So here you'll notice I'm looking for points that are on a curve that are also on a given plane. In other words, I'm looking for the intersection of this parametrized curve with this plane whose equation I have. So, in particular then, notice I have a point generator describing the line, and I have a point tester describing the plane. So, the way I'm going to find the intersections is I'm going to generate points, and you can see that happening right here for any given value of t. Here are the generated x, y, and z. I'm going to take those generated points, and we're going to test them. That you see right here. Right? So again, we are considering all possible values of t. These are the formulas for what's generated, and these points generated by the curve, I just compute this expression 2x plus y minus z, and I ask if this is true. This equation over here on the far right then is how I test to see which of the generated points on the line are actually also on the plane. So that leaves us then with our test is to solve this equation here, and a little bit of algebra, no big deal. We can rewrite it like that, easy to solve. We get these values of t. Now we're almost done, not quite. The question was not what values of t. The question was
what points, right? So don't forget, points are, you can say it two different ways. They're what are generated by the parametrization. They are what we test with the equation. So if what I know is a couple of values of t, right, then in order to get the points that I want, I've got to plug into these equations. So that's the sort of the three-step process. You generate, you test, thus concluding the appropriate values of t, and then you plug in to find what points those actually are. Okay, how are we doing? Everybody happy? All right. Okay. So, now I'm going to go back to the idea of a line in space. We've already seen a line in space previously. In particular, we talked about parametrizing a line in space. And one of the first things I said about it was, well, we can't really write down an equation, right? Because if you have an equation in space, there's three variables, you would expect to get a surface or something like that. And so if you want to make a line, well, a surface isn't really the same thing. So that said, if we can't have an equation, aka a point tester, is there maybe a different kind of a point tester that I might be able to use for a line in space? Not an equation, but how would I test? All right, so here's the argument. We have, again, parametrization, point generator, and here's my test. This is going to seem silly, but it's going to get better fast. And I have to, before I get into the details, I better explain this terminology here. This is a shorthand, this backwards capital E is a shorthand math notation for there is, or there exists. And this weird little symbol here is shorthand for such that or so that. A standard math notation, so you'll see that elsewhere, I'm sure. Okay, so here's the big test. If you come to me with a point x, y, z, and I want to test whether it's on my line, I need to know if there's a value of t such that the point in question actually gets generated by the point generator. And it seems like a silly thing to say, well, of course that's the test, but it's not much of a test, right? It's on the line if it's a point that's generated by the point generator. What do I do with that? How do I actually proceed from that point? Hard question. Okay, so the thing is, I can rephrase this in a way that makes it really easy to work with. And it involves rewriting some of these equations. So in particular, let's look at this first, what I'll call the first coordinate equation. And keep in mind, if you have a vector equation, that's actually three scalar equations. The first coordinate equation has to work, second coordinate, third coordinate, individually all have to work. So the first coordinate equation is x equals x naught plus ta, and I can just solve for t, which gives me this equation. I didn't really do anything there. I just kind of rewrote that equation. And then likewise, this second coordinate equation, I can kind of solve for t there. That gives me this equation. And then the third coordinate equation, I can solve for t there. And that gives me this equation. Now, let's look at our test again. This kind of useless test, not clear where to go from there, is now in this form. And let's think it through again. This says there's some value of t that's equal to this expression and this expression and this expression. Now, just let's step back for a second. How could one value t, a single value t, equal to all three different things? One number can't equal to several different numbers. But it can equal to several different expressions if those expressions are all actually the same. And so that's the test right there. If t is going to equal to three different things, then I need these three things to equal to each other.
That's the test. Oh man, I just did. There we go. That's the test. If t is going to equal to all three of these things, then those three things just have to equal to each other. And then t doesn't have to equal to three different things. Now t is equaling to three identical values. Namely, t is just equal to that value. Okay. So that's, you'll notice this is a point tester. I can take some unknown point x, comma y, comma z. Give me 2 seconds. And I can just plug in, and if all of the equations work, then yeah, there is a value of t. T is whatever that value is that all three of these things are equal to. If these equations don't all work, let's suppose that equation fails, but this equation works. Well, now t would have to equal to, on the one hand, it would have to equal to whatever that is. On the other hand, it would also have to equal to this different thing, and t can't be two different things at the same time. Yeah, question.
So, like, how does this relate? Can you explain the point testing part of it? Like, what's going on here, but like, what is the big picture?
Yeah. So let's go back real quick to the equation of a plane. Here's the equation of a plane, right? A sample plane. And what I mean by this is a test is if you come to me with a point x, comma y, comma z, and you want to know is that on the plane, what you're going to do is you're going to take these values, you're going to plug into there, and you're going to see if the equation works. Right? So we're doing the same thing here. I claim that this is a point tester in that if you come to me with a point x, y, z, right, and you want to know does this pass the test, I'll take these values, I'll plug into there, and I'll see do both of these equations work. If they both work, yes, the point is on the line. If either equation fails, no, it's not on the line. Does that make sense? Yeah.
Practically, would x not a, y not b, so on be given, or would you have to find it yourself?
Yeah. The presumption is that this is a given parametrization. So if this actually is a parametrization, then I have to know all of these things to know what that's parametrizing. So likewise, yes, the x naught and the a and the y naught and the b, etc. Those are all given. Yeah, right, or known or something. Yeah. Okay, so this is called the symmetric equations. Let's see here. I'm making a mess as usual. This is called. This is the symmetric equations for the line. It's a point tester for a line, and we just talked about now how this, how the argument goes that turns the point generator into the point tester. Now, next question. Suppose I have the point tester. Suppose I have the symmetric equations, and I want to know what is the parametrization. How does that argument work? By the way, it's not an argument to just kind of write it down and be like, oh, okay, I'm just going to kind of copy this A. I guess I'll put that there. Right? That's not really an argument. Right? So the way the argument goes, though, given a point tester, is to remember that where that test comes from is that the reason why these things have to equal to each other is because they all have to be equal to t. And once you have this, then, for example, that tells you your formula for x. Just solve for x. Likewise, this is your formula for y. If you just solve for y, etc. Likewise for z. So that's how you go sort of the other way. Yes.
I'm sorry, I might have missed this, but what is the symbol after the t supposed to be?
Oh, yeah. This is a shorthand, a little mathematical shorthand. It means such that or so that.
Is it just like backwards?
Yeah, we've got a combination of a weird symbol and my bad handwriting. Let me try to do a better job here. It's supposed to look like that. Backwards element. Yeah. It's like that. Yeah. Yeah. No worries. Okay, so moving along, we're going to go into section 1.3 now, talk about dot products. Dot products, something that y'all definitely have seen before. I'll remind you, tough choices, pressed for time,
I gotta have to leave some stuff for y'all to read on your own, review on your own, etc. And this is one of those things. Y'all know the dot product. You've seen this formula. There's many properties that you can remind yourself of. They're in the book. There may be others that you saw in Math 218 or 221, depending on which one you took. But make sure to review and polish off those memories. And just while I'm here, I like to throw out I think this is a nice cultural point. Dot product is not just good for what you can do with the dot product. The dot product is also, it's the model for this much more sophisticated idea called an inner product. And you may recall from linear algebra that there you can talk about various different vector spaces on which you might have, for example, an inner product. There might be several different choices of inner products, but the combination is called an inner product space. And there are some really remarkable things you can do with inner product spaces. So my favorite example to talk about, and I have a couple. Anyway, the one I'm going to talk about here is image compression, and that's a pretty hot topic, right? Anyone who watches Netflix, right? You're benefiting from image compression, and if you dig in to see how image compression works, not that it's a single method, right? But one of the big ideas for image compression is an idea that involves using inner products, a very cleverly chosen inner product on a very specific vector space. So anyway, dot products are the sort of the foot in the door that leads to that extremely powerful result. Okay, so I do want to talk a little bit about language. I'm sure y'all have long since heard the word perpendicular. You've also probably recently heard the word orthogonal. There's a little bit different. Our book, best I can tell, seems to use them interchangeably, and I don't think that's a good idea. In fact, there are two separate ideas that we need to distinguish. There's the geometric idea of two vectors defining directions between which the angle is a right angle. Right? That's a geometric concept. It's about directions and angles. Intrinsically geometric. And then there's this closely related, but fundamentally algebraic idea that sometimes a dot product of two vectors is zero. And it's tempting to say, same. But it's not. Very importantly, dot product can be zero even if one or both of the vectors are the zero vector. No problem. There's nothing wrong with that. Right? Whereas perpendicularity, perpendicularity doesn't make any sense if you're talking about a pair of vectors where one of them is the zero vector. Because the zero vector doesn't point. It doesn't define a direction. So what is the angle between the zero vector and some other vector? It just doesn't make any sense. There is no angle to talk about. Right? So these ideas are different because one permits the possibility of a zero vector, the other doesn't. So I think when you have two words and two ideas, you should pair them up, right? And it doesn't make any sense to blur this distinction. So I think the long-standing tradition is to use perpendicular to describe the geometric idea here. So perpendicular means non-zero vectors only. Orthogonal means any case in which the dot product is equal to zero. Hey, maybe some of the vectors are zero, maybe they're not, whatever, don't care. So, two words, two different, closely related to be fair, but still different concepts, and try to do your best to use the right word for the right circumstance. Sometimes you specifically want to exclude the zero vector. Right. Sometimes you very much don't want to exclude the zero vectors. Sometimes you need to allow the zero vector. So in that case, orthogonal would be the right word, and perpendicular would not make sense. Okay. Everybody good on this? All right. Okay, so y'all have probably seen this one before. It's a really easy little construction if you have a non-zero vector and you want to find the unique unit vector pointing in its same direction. Really handy-dandy little formula. You just divide the vector by its own magnitude. Pretty easy to buy that this would work. I hope you've seen it. I hope you've got this formula nicely memorized. And not much else to say about that. Here's something you very likely haven't seen, but maybe you have. That's the idea of a component. Now this addresses a particular scenario where I've got a vector whose purpose, its role in this story, is just to define a direction. This is the direction that we're going to, if you will, kind of care about, and other direction, this other direction, that way, I don't really care about those directions. So in particular, if I've got a vector W and I want to know how much does W point in the relevant direction, right? How much does W, here's the part of W that I actually want. I want to know that it points that far in the relevant direction. That's what we call the component in the V direction. Or we might say, it rolls off the tongue easier to say the V component of W. All right. Now notice that kind of ignores all of this, right? To some extent, W points in the perpendicular direction. Don't care. Couldn't care less. Okay. All right. So this is called the V component. How are we doing? Does everybody see the picture? All right. So there is a little bit of trig you can write down very conveniently. Notice that the magnitude of W is the hypotenuse of a triangle, and notice that, let's see, I'll use green here, the component that we're interested in is another side of that triangle, and therefore the cosine of that angle is that ratio. So really easy little trig there in the picture. Gets you an equation that involves the component. You can then solve for the component. You get this formula here. And you can use that formula to compute the component, but most of the time it's not an easy one to work with because, look, you're going to have to find the angle. What if you don't know the angle? How would you find the angle? It's going to be a little bit of work to find that angle. So the easier trick, rather than finding that angle, is to do this little slick move where you take that given expression and then you multiply and divide simultaneously by the magnitude of V. And doing so, notice, very conveniently, having done that, the numerator is exactly the dot product. And so we get this very nice, much more useful result that you can use this dot product formula to compute components instead of dealing with trig. And roughly speaking, the point here is that the trig involved in the component calculation and the trig involved in this dot product calculation, exact same trig. And so, you don't need to do it at all. We're just looking for a relationship between these things. They have the same trig. Great, cool, noted. And the calculation doesn't involve it at all. Yes?
So I thought component was the same thing as projection.
No.
But it's like the scalar.
Its component is a scalar. That's right. Now, on the next page of notes here, we're going to talk about projection. And I should also note, I suppose, that different books maybe give slightly different definitions of component and projection. And so always, I think it's a prudent choice to always double check what sense of these words is being used in whatever context you see them. But in this book, and therefore in this course, component is a scalar here, and projection we'll talk about on the next page. Is that cool? Yeah. Right. Okay, handy dandy formula. Now, there's an even better version of this formula, in my opinion. That is to note that instead of thinking of this as a dot product, where I then divide by a magnitude, notice that I've got right here V divided by the magnitude of V. That's a unit vector. I am effectively dotting with a unit vector. So whatever I'm trying to find the V component of, I'm just dotting blue dot yellow. That's how you compute component, right? And so this component here, well, let me do it like this. Component, I think it rolls off the tongue very nicely to say components are dot products with unit vectors. This is how I remember the formula for component. Frankly, when I first saw this and I was trying to remember this formula, while you're in practice of doing a calculation, it's a little precarious. You might accidentally do V dot W divided by the magnitude of W. You might just, oops, and get it wrong. I find that really easy mistake to make. But here, no problem. If you want to know the component, well, you dot with the unit vector defining the direction. After all, the V's only job here is to define the direction, and U is the unit vector that defines V's direction. So my batting average on getting that right went from, 800 to, 997. I feel like I'm pretty good at this point, right? Everybody makes mistakes, but I think this makes it easier to remember. Okay, how are we doing? Everybody with me? Yes?
So the unit vector you use should always be the one associated with it?
Yes, that's right. So unit vectors are, in many cases, including this one, unit vectors are a pretty natural way to define directions. And remember, that's the only thing we needed V for anyway, was to define the direction. So yes, absolutely. Just what you said. Okay. All right, now somebody asked about projections. Here is the very, very closely related discussion. Notice the picture looks practically identical. Again, we have a vector whose job here is just to define the relevant direction. We have another vector that, we want to know how far does that vector point just in the relevant direction. And the difference is that projection is not the scalar amount in that direction. Projection is the vector itself. So it's like if you could imagine, it's like you're taking this vector W and looking at its shadow down here on the green line. Okay. So now, how do we find the formula for the projection? Again, closely related to component. Well, this is the way I think about it myself. Projection, being a vector, it has a direction and a magnitude. And both the direction and the magnitude are pretty easy to write down. The direction, unit vector. Right? Unit vector, easy formula. And then the magnitude, namely that length, and that length is the component, which of course I have, I keep missing here. I have that formula for. So now again, this is a formula that you can memorize it, I suppose. I never have. This is just a me thing. I'm not good at memorizing rote. I'm really good at remembering ideas, right? But anything that's rote, I'm gonna transpose. I'm gonna get something backwards. I know it is, but it's really easy to remember the idea of direction and magnitude and pre-existing formulas that we've already memorized, and we're good. So this is what I encourage. You, of course, you'll know yourself better than I. And do what works best for you. But anyway, point being, the projection formula to remember is this one right here. All right. Now, real quick, the book takes a different point of view on this. The book carries it a little further, if you will, and points out that, hey, this unit vector, I have a formula for the unit vector. And, there it is again, that same unit vector. We have a formula for that. And then you can take this, let's see here. This, you've got a magnitude and another magnitude. We call that magnitude squared, which of course is a self-dot product. The other point is you can manipulate it around. And if you prefer, then here's your alternative formula. for the same projection. And it works just as well, no problem, whichever one you like. I'm going to make the case for the one that I gave you first. This formula I gave you first, you can understand it in terms of the pieces that make it up. That is a component. It's something. It's a natural quantity, right? It's something you already know. This is the unit vector. Everything makes sense in that formula. Whereas, on the other hand, if you come down here and ask, what is this thing? It's not really anything natural. It's just, it's the formula for what you have to multiply by V to get the projection, and so that's fine. But it's kind of a disconnect. So I find this formula down here to be a little bit less desirable, and I find this formula up here to be much more desirable. This is the one I always go off of this formula myself. Again, suit yourself. Yes. It's a really tough question. The best answer that I have for you there is actually this right here. So you can take this as a statement about how to interpret components, but you can also view this as a statement about how to interpret dot products. Right? In other words, if you want to have a dot product is this thing, something you can point to, draw a picture of. Right? That's the best I got. A dot product. With the understanding you're dotting with a unit vector, at least, a dot product is a component. Yeah. Dot products in general are this kind of weird scenario where I can't really draw a picture of a dot product. A dot product is just an algebraic construction that relates to other geometric objects, but it itself is pretty hard to see as being its own separate geometric object. So that's why I say tough question. This is my best answer. Yeah. All right. Okie dokie. Last thing before we go on to the next section. Y'all may recall, flashback to high school geometry, there's various facts of plane geometry that you can prove by going to significant trouble, and y'all remember there's some hard proofs in plane geometry. It turns out that some of those are much more easily done with vector algebra. Once you know vector algebra, it's a more powerful tool. It's a little bit unexpected even how it works so well. The big lesson here, of course, is that algebra is a powerful tool. Anytime that you can write things as algebra, it's an extra tool to work with, and it's just going to increase your ability to do things. So, quick example, y'all may recall row reductions from linear algebra, right? And you can strategize about linear algebra, about row reductions, and hey, start with the left column and pivots and all that nonsense. But if you want to actually prove stuff about row reductions, one of the big, deep points of how you really get your foot in the door there is you define these things called elementary matrices. Do y'all remember elementary matrices? It's just a notational alternative for how to write row operations. Arguably, it's just a different way to think about it, except with elementary matrices, they're part of an algebra. We have algebra of matrices and the associative property of matrix multiplication, etc. Really useful. And so there's a lot of facts about row reductions that ultimately you prove by taking something that that isn't written in terms of algebra and just finding a way to rewrite it in terms of algebra. So same thing here. And if you're looking at, for example, you've got some thing like you've got a couple of edges like that, and maybe this is part of a pentagon or something. You can think of this as just being an edge, or you can think of this as being represented by a vector. And this over here, again, you can think of that as just being some edge, but you can also think of it as being represented by a vector. And therefore, you've got in the story now, you see you've got a vector addition. Algebra has showed up because I chose to view these, edges that are connected at a point. That's kind of a clunky, it's a non-algebraic thing. And now I've got it in an algebraic form. Big foot in the door, you can prove a lot of theorems. So there's a couple of nice examples in the book. Take a look, please, and working off of those as kind of guiding examples. There's a homework exercise, at least one homework exercise that you're going to solve by similar methods. Okay, so on to cross products. So there's a bunch of topics in here that we have to go through. Two things I'll say about it. First of all, I'm going to do the topics in a very different order than the book does. And the reason for this is I think my order makes more sense. I think it's more geometrically satisfying. It's got a lot less sort of like massive algebra to be dealt with. There's a couple of tricky observations in what I'm going to do here. But ultimately, I think mine's got a lot less of the opaque, massive algebraic calculation than the books. So anyway, it's a personal preference. Kali has her reasons for wanting to do it that way. I have my reasons for wanting to do it my way. And so there's good reasons for both. Okay. So the second thing I'll say is tough choices and all that. This section takes too much time if I cover all of it. And so I'm going to skip some of it. And in particular, I'm going to skip the proofs. And furthermore, you're not responsible for those proofs. And I can't remember if I hope I noted this I'll have to double check that I had noted this on the content syllabus. But you're not responsible for the proofs that are in this section. Now let me look back at that after class. So anyway, it's unfortunate. We just don't have enough time to go through them. Okay, so I'm going to start off by talking about the order of a list of things, and specifically a geometric characterization of the order in which I've written down a list of things. Okay, so here we go. Here's a list of two things. That's two vectors. By the way, this is starting off in 2 dimensions only. And I want to emphasize what I'm going to talk about here is not the set. I'm not interested in the set, including A and B. I'm interested in the list. The list implies the order. It implies which one is first and which one is second. So specifically, A in this list I have written down is not just one of the vectors in the list, it is the first vector in the list, and B is the second vector in the list. All right, now, having chosen to write A first and B second, geometrically, how would I describe this order? Does the order itself have any sort of geometric, meaning? And the way I like to think about it is, all right, well, let's see. If A is first, there it is, and if B is second, for example, let's suppose it was this. Then, well, this ordered list with A first and B second, notice counterclockwise. At least for, if A and B are those vectors, then that list is counterclockwise. That makes sense? So this is what we call a counterclockwise list. Now, on the other hand, sometimes, maybe, the A vector might be a different vector. Maybe A is this vector. Maybe B is this vector. Both different vectors. And now, A first, B second. That's a clockwise list. Does that make sense to everybody? Okay. All right, now there is a third possibility, and this is annoying, but sometimes a list is neither clockwise nor counterclockwise, and there's kind of different versions of it. You might have something like this where, they're pointing the same direction. And so there's no clockwise or counterclockwise because there's no turning happening. There's just it doesn't make any sense, right? Another possibility, this is just the one I drew here. Another possibility is that A could be the zero vector. And again, there is no direction, and so I just can't make sense out of clockwise, counterclockwise. Likewise, B could be zero. Likewise, they could both be zero. In all of these sort of, if you will, other cases, the vectors are linearly dependent. So these are your three possibilities for a list. A list of vectors in R2, two vectors in R2, clockwise, counterclockwise, dependent. All right. Okay, now I claim this is actually a pretty natural way to describe the order. This natural way to describe the order has some nice properties. So, for example, they are mirror images of each other. So, for example, here's a line over which I can reflect. And if you have a counterclockwise order, such as I do there, A first, B second, that's counterclockwise. If you just reflect that over and look at the reflection, A prime and B prime, notice that that's clockwise. So the reflect, if you will, loosely speaking, the reflection of counterclockwise is clockwise. And vice versa. Everybody good? Okay. Alrighty. Alright. If you have a list and if you trade the positions, so you put the A where the B was, the B where the A was. If you trade, that always changes the order. Now, notice in this example here, the vectors themselves have not changed at all. It's the exact same A, exact same B on both sides. What's changing is the list, right? So, let's see here. A first, B second, you see is counterclockwise. Whereas B first, A second is clockwise. So trading positions changes the order. Okay. Alrighty, and then third, the order is independent of rotations. This one I think is pretty believable. Starting with here a list A comma B. You see here that that's in counterclockwise order. If I were to take this whole thing, if I were to take this whole picture here and just rotate the whole thing, everything in this picture gets rotated by, whatever that angle is, just rotate the whole thing over. Well, then I get two different vectors, R of A and R of B, and, well, naturally, that list also counterclockwise. Right? I mean, pretty believable. If you have if I had a clock here, right, and the hands are going around a certain direction, if I just kind of turn the clock, the hands are still going the same direction. Right? So that's all that's really going on here. How we feel about this? Okay. All right. This is in two dimensions. We have a notion of a geometric notion of order, and we have various properties that this notion satisfies. Now we're going to jump it up to 3 dimensions. And we're going to talk about lists of 3 vectors in 3 dimensions. Is there something kind of analogous in 3 dimensions, kind of analogous to clockwise, counterclockwise? And it's a pretty hard question. If you don't know the answer to this question, if you've never seen this before, this would be a pretty challenging sort of like creative thinking exercise to come up with such a thing on your own. But here's an answer that works great. And it's right-handed and left-handed. And I'm going to have to demo with hand gestures exactly what this means. But this ends up playing a role kind of like clockwise, counterclockwise. So here we go. Let's start with right-handed. What does it mean for a list? A list of vectors to be right-handed. Okay. So it involves the right hand in using your fingers to make a certain gesture. The rules of the gesture are that your index finger has to point parallel to your palm. Your middle finger has to bend only in the way that middle fingers want to bend. So no fair doing stuff like this. Right? So only bend the middle finger inward toward your palm. Index stays parallel to the palm. Middle finger bends toward the palm. And then your thumb, of course, points the way it wants to. And again, you could torque your thumb down like this, just disconnect it or whatever, but no fair. Thumb has to do what it wants to do. Okay, so here's the deal. Given your list, we've got A first, B second, C third. First thing you're going to do, point your index finger in the direction of that first vector. You can see here I'm trying to mimic what A is doing on the page there. A is in the direction of that first vector. Middle finger represents the second vector. Bend your middle finger such that it's pointing in the same direction as that second vector. Again, second vector is B, which is this guy. Okay, everybody with me so far? First vector, second. Okay, here's the thing. Before we go to the third vector, these first two vectors define a plane. Right? Two vectors define a plane. Your thumb points clearly on one side of the plane as opposed to the other side of the plane. If the third vector, C in this case, if the third vector is on the same side of the plane as your thumb, then that is what we call a right-hand order. Right, so this works, right? So we've got A, B like this. My thumb points kind of what you might call on the upward side of the plane. Well, so does C. C appears to be pointing on the upward side of the plane. So victory, right-handed list. A, B, C for this arrangement is a right-handed list. Now, just by contrast, let's look at this other list over here. Let's ask, what can we say about that? Is that a right-handed list? We'll play the game. Let's see here. Keep in mind, A goes first. All right, so fine. A, again, first vector, A, in the direction of your index finger in the direction of that first vector. Now, it's tempting to say I can't get my middle finger to point in the direction of that second vector. Wouldn't I have to bend it? I actually don't. Keep in mind, there's no rule that says you have to keep your hand kind of arranged like this. You can turn, you can do that. Right? And now you see I've got my index finger in the direction of the first vector, but now I can also bend my middle finger following the rules, bending the way it's supposed to bend, and now I've got my middle finger pointing in the direction of B. But the problem is that now my thumb is pointing clearly below the plane that these two vectors define. The thumb is pointing down, C is pointing up. That's a mismatch. This is a fail. And this pair of vectors here is not right-handed. I said pair, I meant trio. This list here of vectors is not right-handed. But it's left-handed. Everybody see that? So index, first vector, middle finger, second vector, thumb pointing up just like C is. Victory. So this is a left-handed list, not a right-handed list. Is everybody with me? Okay. Alrighty. So, and then of course there's the annoying sort of, relatively rare, but it happens sometimes, kind of other scenarios where neither one of these things really works out. Here these vectors are all parallel to the same plane, and there's just, you lose. This is neither right nor left. It just doesn't fit with either one. Question?
Did you try to figure out whether an ordered list is right-handed or left-handed to figure out which direction the cross product is pointing in?
Well, you're getting way ahead. There is a statement that we can make about cross products and handedness, but I don't want to. I guess I'll say that and everybody else should ignore this because we haven't gotten there yet. But if you have A, B, and you want to take a cross product, A, B, cross product will always be a right-handed list or possibly dependent if one of the vectors is 0. Yeah. But yeah, that's ahead of, right.
So what is
What's the other purpose of handedness? There's some cool facts that we're going to get to, I'll say in a few minutes, but I think what that means is on Friday. But yeah, we'll get to it. But what I want to get to real quick before we finish class, all the same properties that we've already observed about clockwise, counterclockwise, hold. So right, left-handed are mirror images of each other. Easy demo. See, my right hand, my left hand, they're mirror images. I think that's easy to buy. Secondly, if you trade two of the vectors, now arbitrarily, no particular reason, I'm going to again trade A and B, but I could have traded A and C, or I could have traded B and C, whatever. When you trade, thus getting a new list, if the initial list was right-hand order, as this is, the new list will be the other. It'll be left-hand order. And so this change from right-hand to left-hand is a result of trading those two positions. And it works for whichever two you move. Okay. And then lastly, again, rotations don't make any difference. And I think, again, real easy to buy, right? So like, if this is my representation of a list of vectors being right-hand order, if I rotate the vectors, well, it's still my right hand. So how you rotate the vectors around, whatever, I can still model it with my right hand because I can just rotate my right hand the same way I rotated the vectors in question. So rotating does not affect order. So, all right, and now we're out of time. That's a nice place to draw the line at the end of this page here. See you on Friday, and I will keep an eye out again for the homework item on GradeScope. See you later.